This is called Ehrenfest theorem, and this is a central fact in quantum mechanics. It tells you that the expectation values follow classical mechanics. So we learned this simple fact that quantum mechanics is based on projective representations. Hi, welcome back everyone. Hope you had a brilliant last couple of days since last time I posted a video on quantum mechanics. First things first, for those who are joining us for the first time, here we follow this book on quantum mechanics. We learn quantum mechanics together, and we follow this book by David Griffiths called Introduction to Quantum Mechanics. Roughly the level is for young undergraduates and advanced high school students. So in these videos I make things really explicit. I do explicit computations so that you can easily follow. And if confusions persist or if there are some clarifications to be done, you can reach me at this mail ID where I take mails. I generally check once a day. um, so for those who have been with me, I have talked about having tutorial classes for this course. So here goes. So this is the first tutorial class that I sort of planned, and these would be based on the last 4 lectures that I uploaded on the channel. Okay. To access these videos, you can, I mean, in the description box I would have a link for my playlist, so you can take a look there. Much more details would be there, but in the tutorial class I would directly borrow formulas that I have already discussed in these videos and try and work out a couple of problems. So that's sort of the idea today, so that it really hammers home all the things we have been discussing the last 4 classes. So this is going to be just a computation, or just a video on computations. Okay, so pen and paper out right now. Okay, so I'd solve one problem on probability and one problem on quantum mechanics live with you guys. So here goes. So let's try and let's use the formulas that we have learned in the last few classes. And the first problem that I want to solve, this is also a problem that was recommended in the book by Griffiths. So imagine someone gives you the wave function, which is a e to the power minus lambda mod x e to the power I omega t. Say someone gives you this, and the exercise today would be to find a. Firstly, this would be done via normalization, which we talked about in our videos. Normalization of the wave function. If you have forgotten what it is, kindly do a brief recap in the videos that are already there in the playlist. And B, find out, after having found out what A is, find out 1, the expectation value of x, the expectation value of x square, and the standard deviation. Recall that a similar problem I've already solved live, right, in one of the last videos. Okay, but nevertheless, let's do this as a brief recap again of what we have learned. So first, how do I what is this normalization that I mentioned? This normalization that I mentioned here, well, you guys know it already, right? So this normalization is done via this equation. And recall why it is the case, because this in quantum mechanics denotes probability, and we know that the probability sums up to 1. So that is the one on the right hand side, that is this one, and this gives you the probability density. So that integrated over gives you the probability. So this has to be 1. So once we have this equation, this helps us fix A, right? So given psi, given the wave function here, of course somebody has given it to you, and generally you have to find out by solving the Schrodinger equation, but that comes later. Imagine someone has given you this wave function, for example. So with this psi, this integral I, note that this is modulus, which means since this is a complex number, this is complex, right? Because of this factor here. So this I now becomes, I should clarify, this A is actually real, so is lambda. Actually, it should be positive. So immediately I can write what this expression means. This expression means A square tx minus infinity plus infinity. Well, this is immediately where I should pause, because you have a modulus here. You have a modulus here, so you know what to do from high school physics, right? You need to break this integration up in two parts. One is A square I have pulled out. It gives you a to the power minus 2 lambda minus x, right? Why? Because x is negative here. So this mod x is actually minus x, right? Plus A square, the remaining part of the integration, right, from 0 to infinity, dx e to the power minus 2 lambda x. Note that once you take the modulus, this modulus here, this phase actually cancels, right? Because this modulus means, I'm being absolutely pedantic here, this modulus means psi star psi, and in psi star psi, this phase factor actually cancels. This phase factor actually cancels. So that's why you don't have it here and here. And the 2, because this is square, this is square. So that's the origin of this 2. Great. So now you can perform these integrals, and these integrals gives you 1 by 2 lambda plus 1 by 2 lambda. You should perform this integral on your own and check that this is what you get. This is very simple. So this I is actually A square by lambda, and therefore I immediately figured out that A is actually, since this I has to be 1, so A has to be root lambda, when lambda is positive. Great. Do you agree? So this was the first part of the computation. Let me paste it here. I have some space. The second part is figuring out, say, for example, mod x square, etc., and the standard deviation, which by definition is the square root of mod x square minus mod x. And these were discussed in lecture 2, if I'm not mistaken. The lecture that was titled Probability Theory. So, and the definition of x was given by, again, this has been priorly defined in the lectures. This is defined by dx x. This is definition. So this is definition mod psi x comma t whole square. This is definition of the expectation value of x. So you have to play the same game again. A square. You have to break the integrals. Minus infinity to 0 dx x e to the power 2 lambda x plus 0 to infinity dx x or minus 2 lambda x. Exactly the same as we got here, right? Except that now I have a x sitting here and an x sitting here. There are two ways of actually dealing with this integral. You could argue that the integrand is actually odd under x going to minus x. Check. Integrand is odd under x going to minus x, which means the integral would be 0, right? Because you're integrating from minus infinity to plus infinity. Or you could simply perform individually these integrals, which is exactly what I would do. I would not be too smart here. I would blindly evaluate these integrals. So the first integral is actually 1 by 4 lambda square. This is 1 by 4 lambda square. So as expected, this is 0. Why is it expected? Because this integral, you can check that this integral is actually odd when you have an x here. This is odd under x going to minus x. So expectation value of x is 0. What about expectation value of x square? Again, using the formula that we have derived in our previous classes, it would be minus infinity to infinity dx x square mod psi x t square. And we can perform the same steps. I'll give you the final result, which is s square 1 by the individual integrals give you 1 by 4. This is an intermediate step. You should check this, that the individual integrals here, the way we broke it into two parts, the individual integrals give you 1 by 4 lambda cube. So this is, simply put, a square by 2 lambda cube. But I know what a square is. I know a is root lambda from here. Which means this expression is actually 1 by 2 lambda square. Good, then we are almost done. So standard deviation, we know this formula, right? If we are using a pen and paper right now, write it down with me before I do. It's square root of the mean of the square minus the square of the mean, right? And we have individually calculated this object and this object, so we know the right hand side. So it is 1 by 2 lambda square root, which is 1 by root 2 times lambda. So this is the standard deviation of this distribution. Okay, so that's the first exercise. If you want, you can actually plot this PDF. This PDF sort of looks like this. Don't mind my drawing, okay? This is psi xt. This is your x-axis, and it's of course symmetric. Yeah. What do I mean? I mean plotting this expression. Plotting the expression here, psi xt. Of course, you cannot plot the phase factor, right? Because it's just a two-dimensional plot. So this is actually, say, without the phase factor. I mean, without. This is a plot without the phase factor. Actually, this tells you a crucial thing about quantum mechanics. This is an aside, which means for those of you again who are joining me for the first time, aside means that even if you don't understand what I'm about to say now completely in complete details, it's fine. It's something that you will gradually learn over the years or when you take up more advanced studies. What is that aside? The aside is that you see in this entire derivation, this phase actually played no part, right? Or in other words, if I had a psi, for example, if I had a psi star here, xt, with the same real part, but a different phase factor, say something like, say, t, it would have given you the same probability, right? It would have given you exactly the same physics. So, and why is that? As you saw, the reason for that is simply the fact that here, for the probability interpretation, you have you basically have a mod square. So any such phase factor actually cancels out here. The physics is independent of this phase. In quantum mechanics, this is called a ray representation. Or a projective representation. So we learned this simple fact that quantum mechanics is based on projective representations. Or in other words, simply put, it means that if your wave function gets multiplied by an arbitrary phase factor here, then the physics doesn't change. That's the definition of what's called a projective representation. But it was an aside. Even if you don't understand it fully right now, it's fine. You'll slowly get to learn more about it. Okay, let's work out a second problem. Second problem that I want to work out with you guys together is show that dp dt minus v prime of x, prime being means differentiation here with respect to the variable x, differentiation, sorry, differentiation. This is called Ehrenfest theorem, and this is a central fact in quantum mechanics. It tells you that the expectation values follow classical mechanics, right? How do I say that? Well, recall that in classical mechanics you would have F, which is basically derivative of the momentum, right? Say ma, which is m d dt of v, which is d dt of momentum. That would be is equal to the derivative, the negative derivative of the potential, right? This we learned in this part we learned in classical mechanics, this part. So the Ehrenfest theorem tells you the individual variables don't necessarily need to follow classical mechanics, but the expectation value of these variables, they follow the same expression that you had in quantum mechanics, that you had in classical mechanics. And this is very pleasing, right? Because eventually we know that in our modern intuition that classical mechanics works, right? Of course it's correct in some limit. So eventually, even from quantum mechanics, you ought to have some connection with classical mechanics, and this connection is called the Ehrenfest theorem, which tells you that the expectation values actually follow the same laws as classical mechanics. So let's do this. So recall again in lecture 4, I had evaluated this expression for you. So we'll start from there. So this was worked out in lecture 4. If you guys don't recall this expression, you can go back to the lecture and check that this is indeed true. In fact, that led us to associate this with the momentum operator, right? Minus IH cross del del x. Great. So then let's work this out. Starting from this expression, your derivative gives you you're allowed to do this because your integration measure has nothing to do with t, right? So IH del del x psi, this gives you minus IH cross del del x when the derivative acts on the first variable plus the situation where the derivative acts on the second variable. You get this expression. Now use Schrodinger equation to evaluate these terms. For example, the del del t, the Schrodinger equation tells you that this was again derived in the first lecture. This was worked out in lecture 1. This tells you this is IH cross by 2m del psi del x square plus 1 by I in the denominator v psi. So you could take a complex conjugation of this expression, and the i's would pick up a sign. Okay, be careful about that. and v is real here. V is real, so v doesn't change sign. If you do that correctly, let me write the expression that that you should get. You should get this dp dt, you should get as minus I h t minus infinity to infinity dx. Then somewhat of an ugly expression, but such is life. Life is hard. d2 dx square plus I by h cross v psi star. This is a psi star, sorry. Times d psi dx plus psi star. I'm just giving you this intermediate expression so that if you guys are actually working it out on your own, you can check this intermediate step, just to build some confidence as to what's happening. Maybe I just need a bit of space to write this properly so that this is clear. Yeah, I want it here actually. So basically what I have done, just to give you a hint, is that I have just used Schrodinger equation here and in the del del t part here. Okay, so if you use in the del del t part here, in the second part you'll be left with a del del x, which is this, and this is the term coming from the Schrodinger equation. And of course you have a psi star, for example, here, which is the psi star here. Okay, great. So then we can see something immediately, some cancellations. For example, this part cancels with this part, right? By integration by parts. Let me explain what's happening. You see you have a minus here and no minus here, but this operator is del del x square, so it's quadratic. So each time a derivative jumps, you know, you integrate by part a del del x, you pick up a sign, but this is quadratic, so eventually you pick up two signs, which means no sign at all. So this minus term cancels this plus term. Okay, that's what's happening. And a part of this term cancels a part of this term, right? Great. So you are left with this expression apart, because there's a derivative acting. This is not the full term doesn't get cancelled. You are left with minus I h cross minus infinity to infinity till del x. Then you are left with a psi star. Then you are left with a minus I by h bar v prime. That's the part that doesn't cancel. And you're left with a psi here. So this simplifies to minus infinity to dx psi star psi. Note that these are just functions, right? So yeah, n minus v prime x. So the reason I mentioned that is you can actually jump this guy over here. These are functions. Later, when we deal with matrices, we need to be a bit more careful. So you're done. That's it. You have proved Ehrenfest theorem, because you have now shown, this was the left hand side, and let's look at the right hand side. What have you shown? So the right hand side is basically minus infinity to infinity dx. This guy is, say, it's minus vx v prime x times mod psi square, right? So this by definition is expectation value of minus v prime x. So great. Now we have actually shown Ehrenfest theorem, QED. So this is quite remarkable, right? It tells you all the fancy things that we have learned. Actually, the expectation value, again, it's quite important physics that expectation values follow classical laws, just as you proved here, that these are basically what you would get from classical mechanics if you didn't have the expectation sign. And this, as we have argued, or as we have mentioned, that this is actually called the Ehrenfest theorem. So yeah. So maybe I'll stop here. If you guys like the class, then kindly like and subscribe, of course, and share it with your friends who might be interested. And my channel is, as you probably are already following, is Ray Physics Made Less Scary. So see you next time.